Howdy! This is your friendly neighborhood physics teacher here, and we're going to talk about rotating motion. The cool thing about this unit, you know all the base information already. You do. You know about kinematics, you know about energy, and when we get into the next little PowerPoint, you know about momentum, and you know about force. So the base information you know. This is why I really like the fact that this unit is last, because it's a good review over all the different items, and then we're just going to take it that step further and make it have a little twist to it. Yeah, okay. It's y'all love me. It's okay. So retaining kinematics and energy, and then I'll make another video over torque and rotational momentum. Let's focus about this right now. So these are just some key points that we're going to talk about during the video. We're going to make that go away. And again, you know about position, you know about velocity, you know about acceleration. We're just adding angular to the mix. You know about kinematics. We're just adding rotation. We're talking about the difference between linear and rotation. What happens when things are actually rolling. And then, again, you know about kinematics. You know about inertia. Now we just talk about what happens when it rotates. And conservation of energy, nothing changes there. So the definition of angular position. It's where the, pretty much you pick a spot on a, let's say, wheel here. You're just going to pick a spot. And where that spot is from, like, the reference line, and usually you think about your graph, so you make it like the x-axis. So that's your reference point, and how far off your dot is from your reference point is your angular position. Now, we use angular position with theta because it is an angle. Because if we, think about if you think about your, if you're in pre-cal, you go from 0, 90, 180, 270, 360. This is our 0 spot, so that's our reference point. And then if you want to move, you just go a little bit, and you're at some angle. So that's why we use it at an angle, because it's rotating. And we reference it in radians. Now, signs, dealing with, is it counterclockwise or clockwise? If your theta is greater than 0, you're going counterclockwise, which would be that way. If you're going clockwise, it's going to be less than 0, so you're going into the negative. So if you're going clockwise, it's going to end up being negative. If you're going counterclockwise, it's going to be positive. And that's the same thing if you're sitting here dealing with your unit circle here. You're going from 0 to 90, and if you started going that way, and if you started going the opposite direction, it would end up being the same numbers, just the negative versions. And then going from degrees to revolutions. So 1 revolution, which would be 1 time all completely around, of course, is 360. And don't tell Mr. Jones this, or Mr. Sluter. Do not tell them this, that I'm admitting. But degrees is technically, and I know we've used degrees like in projectiles and doing different things at an angle, but degrees is not the true SI unit for things going at an angle. Radians technically is. Whew, glad to get that off my chest, but shh, don't tell them that. Don't tell them I admitted it. So technically we're not supposed to deal in degrees, because, in sciences, we're dealing with all SI units. That's why we use meters instead of miles. We use grams instead of slugs and different things. But degrees is technically not an SI unit. Radians is. So we have to convert everything to radians. Now, we have the degrees. So we have the theta. And like I said, that's technically not in radians. And we want to actually know the length. So pretty much how far it is from here to here. That's not something we can sit there and just take a ruler and measure. It doesn't work that way because there's some type of fun little curvature there. So that's how we can use this lovely radius. What you'll see that radius plays a big part in a lot of the position, velocity, and acceleration. So you would just take your theta, which is your angular position, times it by your radius, and you get your arc length, which is measured in radians. And now, your radius is measured in meters. Your theta is measured in degrees. You multiply those together, boom, and you get radians. So there you go. Now we're going to jump into angular velocity. So your angular velocity is represented with a omega. It's a lowercase omega. I know you're like, oh, that's an omega. That's an uppercase omega, lowercase omega, just like we do. Greek letters do have uppercase and lowercase. And we've used so many Greek letters so far, we have to go definite. This is capital. This is lowercase. We're getting to that point, but it's okay. We got this. So you have your average angular velocity. And just like, if you remember your average velocity, it's your distance or your change in distance, which we use x here, change in distance over our change in time. Excuse me. So your change in distance over change in time. That's for normal velocity. This is your angular velocity. So your theta is just your angular position. So that is your angular displacement. That's all that is. Delta theta is your angular displacement. Like delta x is your displacement, and x is your position. Time stays the same. It doesn't matter if things are rotating, spinning, flipping. Time is just going to stay time. It's very consistent. Thank goodness. And then you get radians per second, or you can just get radians per second does just equal 1 over seconds, because radians is a weird little thing. And so how that does, so if you start from your reference line, you've moved, so your initial theta is you move from here to here. There, come on, pen. There we go, there to there. And then you moved all the way over here. So just like in normal, you do your final minus your initial. Just like if you did your displacement over here. Final minus initial. It's just the same thing. You just, from your initial position and then your final position. But it's all in degrees. And you would just measure that. I mean, if you sit there and had to measure it, you would use a protractor instead of a meter stick like we're used to. And then you just time it, how long it takes it to get there. For your angular acceleration, before we do that, we need to talk about period. You've seen this equation before. Now, this is the first equation that's actually on your formula chart. All the other ones are not on your formula chart. This one is on your formula chart. It's on the short list. So after all what these variables mean, it's on the short list, the second to the top, and it also has, you see this, 1 over frequency. So we've talked about period as 1 over frequency before, but we really didn't get into the fact that period is your 2 pi over your omega, which your omega is your angular velocity. Now, just a reminder what period is. Period is how long it takes to do one rotation. Your period is how long it takes to do one rotation. And if you remember, we said that your period is your circumference over time. And if we break down what circumference is your 2 pi r over t. Well, radius over time, that's just your distance over time. Seeing it? You seeing it? You seeing it? So for here, if we pull, so I'm trying to show you where this equation comes from. I'm just deriving this equation. Do you have to derive this equation? No. Would they maybe make you derive an equation? I don't know. That's why I'm showing it to you. So we have that part pulled out of the equation. Check. But now we need to get to the omega part. Now, your omega is radius times your velocity. So we have the radius part, but we need to get the time to be turned into velocity. If we break down what velocity is, is your distance over time. So that's your velocity. And through your r over t, your distance is already taken care of, and so you get, it's not flipping for me. What am I missing? Email. Oh, try to make them cancel out. It's too early in the morning. My brain. Okay, so that's the same thing, kind of wanting it to cancel out. So that's why you have to do 1 over your omega to make those cancel. There we go. You just got to flip it. Brain needs to wake up. Sorry about that. But hey, you see that when you're sitting there deriving, it might take you a minute to sit there and realize how things work. Whew, brain needs to start working. So now, definition of average angular acceleration. So again, if you remember your acceleration, it's just your change velocity over change in time. This is just your angular, time stays the same, and you just get radians over seconds squared. Here is where the fun part happens. This equation should look extremely familiar. Maybe, change that into a little velocity there, change that into initial velocity, plus AT. I think that is officially the first, if you add little x's there, that is the first equation on your formula chart. That is one of the first equations we learned. But if you scroll down on your list of formula, it's it's that same, you see this equation at the top, and then you scroll down so it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So all the way down, so you're 13, you should see this equation. So that equation is on your formula chart. And you treat it just like your kinematic equation. You treat it just like your kinematic equation. Just now you're dealing with velocity rotating. So instead of like something moving like that, we're just dealing with something moving like that. That's it. That's all we're doing. And things move differently in a rotation because of its movement away from its center point. We learned that dealing with circular motion, that the farther it gets out, the slower it gets, the closer it gets, the faster it gets. So that radius plays a part in how fast something is moving. Of course, I should have drew it over here because that's all zeros. So we're going to come back over here. We're going to erase that. Maybe erase. Nope. Okay, that's just going to stay there. So now you have a acceleration, you have a angular acceleration, angular velocity just up here. Now down here, everything's still just going in a straight line. So all this is a true 1D motion. This, if you're trying to figure all that, just up here in the circle part is where your rotation is going to happen. And you can do that to so you can sit here and here's all your linear equations. So that is on our formula chart. This one's on our formula chart, and this one's on our formula chart. This one is not. That one is not on the formula chart. But when you talk about the big four kinematic equations, they throw that in there. But you got this. You can get this one by combining the last two. You can get that one. So they tend to not put that one on the formula chart. So that being said, for rotation though, this one's on the formula chart. This one's on the formula chart, and these two are not on the formula chart. But the cool thing about this one, it's the exact same thing as this. They're just changing your V's to W or omegas, your A's to alphas, and your X's to thetas. And so yeah, so technically you do have this equation, you just have to remember to convert. But yeah, so there you go. There's just combining the linear equations to the angular equations. Your linear quantity, so that's just position, is your X. We've already talked about that, so that's your angular position. V is velocity, so your omega is just your angular velocity. A is your acceleration, so your alpha is, and this is a lowercase alpha, is your angular acceleration. Now, there is a difference between tangential speed and rotational speed. So your tangential speed is what, when you take your radius times your rotational acceleration, that's what you get. Now, remember tangential speed, we talked about that, is when we're like spinning a ball and we let it go, and that's the direction it goes. So your tangential just means linear. So if you think about like tangent, tangent to the curve, remember that the joke I did? I don't know. What was it? What was it? Something about calculus. I can't remember the joke I said. Something about, something like, are you a derivative? Because I would like to lay tangent to your curves or something like that. That was a bad joke. But your tangential is just, so if you have to the curve, it's just a straight line to, at that point, a straight line on the curve. So you can figure out that's just your linear velocity of an object that's going in a circle. And just like how your X was your radius times your theta, same thing as your tangential velocity is just your radius times your omega. And it's the same thing with your acceleration, but now this is centripetal acceleration. So remember, your centripetal acceleration is the, one that's being pulled towards the center. And you can break that down into rotational versions also. That's just your radius omega squared. But remember what we did, your centripetal acceleration was v squared over r. If we know that v equals r omega, we plug that in. See, equals r omega squared over r. That squared's got to go to both things, so we get that r squared, omega squared over r. We cancel out an r, so we get that it's r omega squared. So that's kind of where that equation comes from. This equation is not on your formula chart. They think if you need to derive that, you can figure that out. So, but since you can use your notes, might as well put that on your one-pager. And it is centripetal acceleration, so that is technically a linear. So your centripetal is linear because it's just going straight down, is meters per second squared. But just putting it into rotational quantities. Tangential acceleration is, again, you just take your alpha times your radius, and you can get your tangential acceleration. Your tangential acceleration would be just, again, if you're at that point, it's going at a straight line. Tangential versus centripetal acceleration. So your tangential acceleration is due to the change of the angular speed. Your centripetal acceleration is due to the change of direction of motion. So those are the two big things between tangential and centripetal, and also like where it is. So if you have a curve, your tangential would be going straight out. So that's your tangential acceleration. Your centripetal is going towards the center. Remember, centripetal acceleration always goes towards the center of the object. So making connections between your linear and your rotational quantities. Your pretty much think about the merry-go-round has both tangential and centripetal acceleration because it's going in a circle. So it has both. Most things are going in a circle, has both. And so to figure out if it just asks, and this is where AP kind of toys with the line, something's going in a circle and it just asks for acceleration and it's not specific like tangential acceleration or centripetal acceleration. It's wanting vectors. So you have to think about your tangent, your centripetal is going that way, your tangential is going that way, and so it's wanting your resultant. And so that's when you have to pull in Pythagorean theorem or sine, cosine, and tangent into the mix. Now, rolling motion. So when something we have just dealt with in dealing with centripetal force and centripetal acceleration, we've just dealt with something rotating and not necessarily rotating and truly moving. So yes, you can talk about a car going in a circle we've talked about, but we've just talked about that centripetal acceleration. When y'all were asking a lot of questions about like, so how does that work with, it moving and the things rotating? This is how everything connects. So if an object is rolling without slipping, okay, so that's the key thing here is rolling without slipping. There is a fixed relationship between tangential and rotational speeds. So your velocity, again, trying to figure out your velocity, you would have your circumference. So that just equals your circumference over the period. So how long it takes to do one circumference. And then to get your tangential would be your omega and your r. And remember your tangent, so it'd be, so your main velocity is mainly coming from the center. Your tangential would be coming from whatever point you're starting with. And your 2 pi, so it's saying if this is your point, how long it takes for that point to get all the way back to hitting the ground, basically. So that's why that's equivalent to like your distance. Now, we may also consider like the actual rolling motion to be pure rotation or pure transitional motion. It's according what you're wanting with that. So like I said, you pick a point and that's your tangential. You can, and any one of these would be your tangential velocity. Now, dealing over here, so again, that's your tangential velocity. But if you're, so you see how like these, like it's going in the same direction. If your velocity, you're counting like this velocity as 0 here, and you're wanting to know how fast, it's moving in general, you're going to have to, reason it's doubled is because there's one here, and they're acting together. So yeah, like they're going with each other. That's why there's a 2 there. So now, energy and the moment of inertia. Now, moment of inertia is a little hard to kind of think about because you're like, inertia is just mass in motion, right? That's what inertia is mass in motion. Well, how different, when we talked about things moving like a ball or anything, we've just talked about like a uniform mass spread out. But most things don't have a uniform mass spread out. They don't. Think about when an ice skater is skating, so when they go to speed up, they pull their arms in, and when they need to slow down, they push their arms out. If you have a rolly chair, like a chair that you can spin in, try spinning. You pull your arms in, you'll go faster. You let your arms out, you'll go slower. And so that moment, the moment of inertia in rotation, I can write moment of inertia in rotation, you have to take the different sizes into consideration. So for this mass, and so it's axis of rotation. So we have pretty much a rod with a mass at the end. And you have to think about all the different energies. So it is moving, so it does have a tangential or a linear velocity. So we do have your kinetic energy for the linear. You can sit there and then you would just substitute for trying to figure we're trying to figure out exactly for rotation. You can substitute your tangential velocity for your rotational velocity. And then all they did was kind of manipulate, because that square's got to go to both. And then you get this part right here. That part takes the mass in consideration and how, because it's squared, because if it goes in a circle, right, it's going to go basically that far direction also. And that right there is your moment of inertia. Right there, that is your moment of inertia. And so we can substitute that in. So we can substitute the mr squared for I. And that equation is on your formula chart. It is on the big list, and it's 1, 2, 3, 4 from the bottom on the big long list. 4 from the bottom. Now, one thing they don't give you is I, because you can see that where I is the moment of inertia given at the sum of the mr squares, there are specific I's for all different masses and shapes of masses. So there's like a T, a bar, a circle, a hollow sphere, a round the edge sphere. I mean, there's in which you'll see in just a minute. And they don't expect you to memorize those. If you need that, they've always given it to you. So look. So just a hoop is r squared. A disk is 1/2 mr squared. A solid, that's cylinder, sorry. A disk or solid cylinder, and you're dealing with, it's like off so the axis is not in the center. You have a hollow sphere, a solid sphere that's not on the at the axis is not in the center. So you have all these different ones that they never made you memorize, because if you needed it, they gave it to you. So this part you didn't have to memorize. I would still, once we start doing one pagers, I would still put this information on the one page. I mean, if it's on your one page, just so you can have easy access to it. And so you don't have to memorize. But these are not on your formula chart. They have never made you memorize these. If you needed it, they gave it to you. But you just have to know that I, once you figure that out, you'd plug that into your kinetic energy equation. Because that's taking how far the mass is off the axis into consideration. Because that's going to change how things spin. And, I mean, you sit there and try to spin something, if your car, if a wheel is not level, you go thudum, thudum, thudum. I mean, there's the reason why you want it to be completely inflated. So, because your car would probably be would blend between, your wheel of your car would be a blend between those two. And, so you want it to be even, so it kind of rolls evenly and stuff. Now, dealing with the conservation of energy, again, whatever energy you put in, you got to be the energy you take out. Now, you're just putting more different types of energy in, because if your wheel is rolling, it's rolling in a linear and rotational motion. So that takes up some energy to make it roll, versus just like sliding and moving in one dimension. So you do have to take both consideration. You have to add those together, and you can sit there and manipulate But yeah, you do have to add rotation into the mix. It's saying, okay, how much energy is a wheel rolling down a hill? You have to do tangential and rotational energy. So for these two objects, same mass and radius, are released simultaneously. The disk will reach the bottom. So basically, which disk will reach the bottom first? More of its gravitational potential, or the disk will go first. And it's because more of its gravitational potential energy is transferred to kinetic and less to rotational. As if we go back to our equation here, so the hoop versus the disc is 1/2 as much as the hoop. So when it rolls down, the hoop, more of that energy is taken into consideration to make it go in a circle because it's farther away from the center than a disc, which it has mass evenly transferred throughout the thing. So that's just referring back to this equation here. They do like asking about hoops and discs and stuff. But pretty much it's just an overall summary. Describing rotational motion requires knowing how your rotational and linear interact. You have a few equations. This is not on the formula chart, but basically it's just your basic version of your linear, This is on your formula chart, knowing that going counterclockwise is positive, clockwise is negative, knowing that linear quantities versus angular quantities, your equations, remember, on formula chart, on formula chart, on formula chart, on formula chart, on formula chart. These are not on your formula chart, but just good to know. Dealing with rolling motion, you have, that's just, I presented it like that. That's just manipulating it for omega. You have your kinetic energy for rotation. You have to take, our mass is a little bit different because we're not saying it's uniform anymore. So we have to take all the different moment of inertias and all the different types of moment of inertias. The big ones to remember is that hoop. These are the two big ones that they do. Hoop is just your regular MR, and your disk is 1/2 MR squared. If things are rolling without slipping, you have to take the linear and your rotational or angular kinetic energy into consideration when solving problems with dealing with conservation of energy. So that's about it for your energy and moment inertia and your kinematic equations. I will make another video dealing with momentum and torque by itself. Hope you have a wonderful day. Bye.